Hello guys, and welcome to this series which is on machine learning fundamentals. We were discussing in fact advanced clustering, and then in that we had taken in fact a DB scan in this particular episode, the previous part of it. We are on episode 16, and this is probably the fourth part of it, and this is going to be the final one most likely. So we are going to discuss, in fact, one of the very interesting and important machine learning models in this category, which is falling in this advanced clustering. And we are, in fact, going through the unsupervised machine learning. We had, in fact, given the comparison of K-means to DB scan as well, and different aspects in which they vary, and what are the application areas of DB scan. So we shall be continuing on the same from the same point where we left, where we in fact in a detailed, meticulous manner we have explained DB scan. We have seen its implementation in Python as well by considering a very simple program, and we had seen its implementation. Now we shall be continuing on this Gaussian Mixture Model, GMM. And first of all, we'll understand what this is, and then after that, we'll be taking its implementation as well in Python. Let me just present this. I'm showcasing the slides which are there. So in advanced clustering, this is Gaussian mixture model, which is GMM. So what is, first of all, GMM? The definition of it. GMM assumes data is generated from a mixture of K Gaussian distributions. So it is assuming that different the data is generated from a mixture of distributions, which it is referring to as a Gaussian distribution. We'll be understanding it, each with its own mean and covariance. So every data point is having its own mean. The data is having its mean and covariance. Unlike hard clustering, GMM provides soft assignment with probabilistic membership. So what we had seen earlier, if you just remember in this DB scan as well, we had seen that clustering is on the basis of the resemblance in the characteristics. We have that is in fact on the density. So the near points which are there, they are clustered. We have seen how it happens in DB scan. But GMM is taking a slightly different approach. It does not hard cluster. That means it is not categorizing and putting the data points into a particular category, groups directly. It is saying the probability of this point, this particular point, to be in cluster A, or to be in cluster B, or in cluster C. So it is just giving the probability. For example, there is a data point. We can take the student's example. A student's example who is having the study hours of 4 and who is having the attendance of 70. For example, this is a data point. Now, this student having the likelihood of being in cluster A is, for example, 70%, and in cluster B is 30%. So it is actually doing this, what we call as the soft cluster. So unlike hard clustering, it is just giving a soft assignment with probability of a membership, that what is the probability percentage of this particular data point to be a member of cluster A or cluster B. So that is the biggest difference in GMM, which we can find. I hope that with this example you would have understood it. We are going to in fact take few more examples in this. So it is saying, in simple words, instead of assigning a data point to exactly one cluster, GMM tells us how likely it is to belong to each cluster. That's what exactly I was telling you. So what is the probability of a data point to be a part of cluster A or to be a part of cluster B? This is called as soft clustering. So this we refer to as what was happening in DB scan or other earlier machine learning algorithms in this category. What we had done is it is categorizing them and placing them into clusters, and then that is referred to as a hard cluster. But here it is just giving a probabilistic membership, that the probability of this particular data point to be in this cluster is 90%, to be in this cluster is 10%. So this is just, probability, or it can be something else. This is just an example that probability is just giving the probability. So to understand this Gaussian mixture model, easy example is there. You can imagine the students grouped based on study hours and attendance, which I had given one example to you. Some students clearly belong to low performing group, high performing group. So there can be groups which are low performing, which are high performing, but some students are in between. For example, GMM says student A 90% in cluster 1. So probability of student A is that it belongs to 90% in cluster A and 10% in cluster 2. Cluster 1 and cluster 2 is there. So 90% probability is there for student A to belong to cluster A based on its cluster 1, sorry, based on its characteristics, and 10% chances are there that this student A will be in cluster 2. So student B is having 60% chances to be in cluster 1 and 40% chances to be in cluster 2. So unlike K-means or hard assignment, one cluster, it will be either belonging to one cluster or another cluster. GMM is just giving you probabilistic assignment. So it is giving the probability in a very simple term. It gives the probability of this data point to belong to the cluster 1 or cluster 2. Well, that is a major difference, in fact, which we can find in Gaussian mixture model. Core concepts that are there: Gaussian distribution is there, bell curve probability distribution defined by the mean and the covariance, so summation, and then this is their covariance, which is in fact explained with a mathematical expression. We are not going into actually that. That might not be that helpful if we don't want to go into the mathematical expression, because we want to understand Gaussian distribution at a fundamental level. Although in certain machine learning algorithms, I have just given a comprehensive mathematical expressions as well. But of late, I realized that, at this level, when we are discussing about the fundamentals of machine learning, that might not be the appropriate approach. So when we'll be utilizing GMM in a specific application area, and there will be a series which will be specifically for that. So at that time, it will be an appropriate thing to take these algorithms in a deeper, way, and explain the mathematical expressions which are inside their mathematical equation, and how it is getting inside the algorithm, how machine learning algorithm is evaluating it, what is the logic behind that. So it will be appropriate there. But when we are discussing the fundamentals, I don't think we should be going into that and complicating it at this level. Mixture, weighted combination of multiple Gaussian distribution modeling complex data. So this is a weighted combination of multiple Gaussian distributions, modeling complex data. So with which we can model the data which is complex. Soft clustering, we have already known that points assign the probabilistic membership across. It is not a hard clustering. It is a soft clustering where the probabilities are associated to the data points, not actually they are categorized into clusters rather than hard assignments. So they're saying, so it's a soft clustering. You need to understand two more, very important concepts which are there: expectation and maximization. What is expectation doing? Expectation is calculating the probability that each point belongs to each cluster. What is the probability? That is what we have already calculated, for example, before. So it is calculated by the expectation. So probability. Calculate probability of each point belonging to each cluster using current parameters. So whatever parameters are currently coming, based on those, what is the probability of a particular data point to belong to any of the clusters? So that is there. And maximization, update model parameters. So this can be variance, this can be means, this can be weights to maximize likelihood given the current assignment. So you are updating the parameters, model parameters. So these two things are coming there. Expectation is the probability, and maximization is the parameters which are there, updating those model parameters so that we can get a likelihood given on a particular scenario. So that is maximization. We are going to see this in a closer way. What is the intuition behind this GMM, Gaussian mixture model? Software cluster membership is one of the main things which I was referring to, and that is the significant differences that we are having. Unlike hard clustering, GMM assigns probability scores to each cluster. A data point might have 70% membership in a cluster A and 30% in cluster B, reflecting uncertainty in boundaries. So you can just see a cluster center. It is showing that, a data point is having 70% probability in cluster to belong to cluster A and 30% probability to belong to cluster B. So that is in fact graphically represented as well on the right hand side, if you can just see. So this is one major thing which is there in Gaussian mixture model. So we can just take an example of the same data set we have seen. You can just see it is taking the study hours and in fact the attendance, and we can demonstrate probability of a particular student to belong to one cluster or the other cluster based on these two things. So it will be demonstrating the soft probabilistic assignments. So soft probability, soft clustering, not the hard one. So definitely now we are in a position to in fact take this example in Python. So first of all, I would just like to again go through this Gaussian mixture model little bit. You can just see we have taken a definition of it, what Gaussian mixture model is. There is in fact one huge you can just say difference, that it is doing the soft assignments, soft clustering rather than hard clustering, which are based on probabilities. And then there are in fact certain concepts. We have given an example of this as well, study for a student who can belong to this. So how the soft assignments are happening, and then there are few concepts which are there, soft clustering, in fact mixture and Gaussian distribution that we have gone through, and maximization and expectation and maximization are the two terms which are there, which are in fact calculated. And soft clustering membership, it is just talking about how soft clustering is happening, the probability. It is giving just the probability percentage. And in fact if you are taking the same example of a student, student performance, then we are having in fact a data point and on the basis of that it will be giving a probability whether this student belongs to probability of this student belonging to one category or the other category. And then let us just have this implementation of this Gaussian mixture model. So this is a very simple program. In the similar manner, we had taken the DB scan. This is also having 5 steps of that. So this is not complicated. We have taken a similar kind of a data as well. We are creating that here itself in the program. You can just see which is having 300 samples. And in fact, then we are scaling the data to a standard scaler, and then we are creating a GMM model here rather than having the DB scan in the earlier case. It is the same example, just one thing we have changed is that we have chosen here Gaussian mixture model. So that is here exactly in the same manner, and we are applying that. We are training the model here and then predicting the cluster. And then we are getting probabilities. So this is here, you can just see getting the probabilities, and we are printing in fact the cluster probabilities. So that is here, and then it is just for the sake of understanding, we are putting one graph and visualizing it so that we will be able to understand this visualize it so that we can have a better comprehension of it. Very simple example, in fact you can just see to understand this GMM. Very important algorithm as well. So let us just go and execute this program. So let me just go and run. We'll be understanding some of the aspects of it while it produces the result as well. You can just see so it is executing this particular program, a simple one, and then it is giving us first 5 points of the cluster. You can just see, I will just show it to you. It has generated this because with this one we'll be able to the output which are in numerics, so it will be in fact generating those, but it becomes difficult to understand from there. But if you see this one, you will be able to understand that it is in fact, GMM is working on this, and it is giving the probabilities of a particular point belonging to this category, and then on the basis of that it is creating. So you can just see feature 1 and feature 2. This program has run, and we are able to understand that what GMM, Gaussian mixture model, has done. In fact, how on the basis of what it is in fact putting these clusters, it is giving a probabilistic membership, or you can just say soft clustering it is doing. So you can just see from here, this figure is in fact giving the GMM clustering itself. So that is here, we are plotting that. And in fact, it is clustering probabilities. First 5 points are there. So how the clustering probabilities are coming, it is giving that clustering probabilities as an output. So that is given there. So in fact, this data which is here, and then which is getting generated, we can have some more examples on GMM. So we'll just see, because I don't want to just put too many of these things in the at the basic level, so that it will be a little overwhelming for the students to for the viewers to understand. So if you just see this clustering, GMM clustering, scattered plots are there. Probabilistic assignments, GMM assigns each data point to a cluster with soft probabilities, visualized here with distinct colors. So these are the soft probabilities which are visualized with different colors. So different probabilities are there. GMM output analysis, each data point receives a cluster label and a probability score indicating membership likelihood for each Gaussian component. So definitely it is putting different probabilities which are there. So these are points in fact, and the probabilities which are there. And then in fact the comparison, if we have to just choosing the right algorithm, each algorithm excels in different scenarios. Choose based on your data structure, noise tolerance, and whether you need a hard or a soft clustering assignment. So when we are comparing, for example, we are going with hierarchical DB scan, or for example the GMM, we need to understand which one is which one is appropriate. So hierarchy detection, noise handling, soft clustering. So based on the particular scenario, use case scenario, we can just opt for which particular machine learning model will be choosing there. And what are the key takeaways from here? Hierarchical is interpretable dendrograms, which we have seen in fact in second part of this particular episode 16. We have seen in that interpretable dendrograms ideal for nested clusters, structures, and hierarchy visualization. So that is, in fact, hierarchical is suitable for that. Then we had seen the DB scan in quite a detail in the previous part of this episode, robust to noise and outliers. So DB scan is actually just giving you the clusters, but they are those DB scan is doing one thing, that it is outrightly identifying the outliers, so which do not belong to a particular category, and they can be in some situations they can be very DB scan can be very useful. For example, in case of cybersecurity, we had seen that anomaly detection or malicious traffic detection. So for that, this can be very useful. We are in fact having a series upcoming which will be on fraud detection, anomaly detection separately. In that one, in unsupervised, we'll be using DB scan, so that outliers are outrightly identified, so that that traffic which is in fact, and especially we have seen that it is that situation where the minorities will be there, because these cases of having anomalies are very less. So in that one, it can be robust to noise and outliers. So this DB scan is very robust algorithm as far as noise and outliers are concerned. No need to specify cluster count beforehand. So that is one more advantage compared to K-means. And then GMM, if we just see soft probabilistic assignments, models complex multivariate distributions. So it can model complex data, complex multivariate distributions effectively. So if you're having a complex data, so which is having variable multivariate distributions, so different data points, variable data points, so very complex multivariate distributions which is there. It can effectively model that kind of data. So we can just have GMM used in that situation. So I think that's it. We are done with these advanced machine learning models as far as unsupervised learning is concerned. We will be in fact coming up next with one more episode which will be focusing on one more significant area of machine learning fundamentals. And probably with that and one more episode at the end as a conclusion is going to be the final episode, maybe 16 and 17 and 18. 18th is going to be final for this one. And then we'll be focusing on in some other series the use of different machine learning algorithms for specifically for different applications. Thank you so much for joining, and please provide us your valuable feedback for how you are getting benefited from this. These in fact these lessons which are there, this series which is specifically on machine learning fundamentals. Please provide your valuable critical feedback so that we can uplift and in fact enhance, so that we'll be able to deliver appropriate and better quality lessons in this area, in this domain of artificial intelligence and machine learning, and some other domains like cybersecurity and others which are there. Thank you so much once again for joining, and please subscribe to the channel in case you think that this is going to be beneficial for you, so that you'll be getting in fact intimation whenever a new upload is done on the channel. Thank you so much once again, and see you on the other side.